Hi all, welcome to another session from Nairo and Srijit here. So today I'm going to brief you about another application of the band module. So how to demonstrate the behavior of a benzene molecule in a magnetic field using band module in AMS. So we will brief you step by step. First of all, I need to focus on the theoretical background of benzene and the aromaticity, of course, of the aromatic compound first ever uh, defined. So it's a cyclic hydrocarbon with a planar hexagonal structure. One of the unique properties is the stability and the reactivity which arises from its relocalized pi electron system, forming a ring current when subjected to a magnetic field. So this is one of the key aspects of its aromaticity. And also speaking about the nuclear magnetic resonance, experimentally, the effect of the magnetic field on the benzene is directly observed through NMR spectroscopy. So the applied magnetic field interacts with the magnetic moments of the atomic nuclei, especially H1C13 in benzene, causing them to align with or against the field. The delocalized pi electrons in benzene create a secondary magnetic field that shields the nuclei, resulting in the characteristics chemical shift in NMR spectrum. So in this session, we are not focusing on the spectrum, we are focusing on how we can computationally uh, prove or visualize this magnetic field of this benzene molecule with the band engine. So speaking about AMS band, it is a powerful software package which allows to simulate the electronic structure and properties of the molecules and periodic systems using density functional theory. It can model the interactions of molecules with the external magnetic field and calculate properties like magnetic current and NMR chemical shift. So how we can set up this simulation in this AMS input? So we need to build the benzene molecule. First of all, I have already done the calculation. I will show you what are the necessary inputs. So I have uploaded the benzene molecule from this database, or we can do the necessary, we can upload the benzene using the builder tool. But here, just I'm uploading it from the database. You can see how I selected the molecule, and then I'm just going back to the main panel. So by default, this setting will be the periodicity of this molecule will be in bulk three-dimensional mode, but we need to change the periodicity to none or zero dimension. And then we need to navigate to this magnetic field in the model tab. So where we can set up the magnetic field calculations, I mean the settings. For instance, we have to apply a certain magnitude, for example, zero point 0.1 Tesla along the z-axis, which is perpendicular to the benzene ring in the plane. The choice of this field strength can be varied to observe its effect. Then we need to select a suitable method for handling the magnetic field, such as non-relativistic linear density of orbital dependent current density function. So we will brief what is actually the purpose of this methodology, which will be effective for the calculations related to magnetic field. So I'm just giving a short description about what are the breakdowns in this method. The first one is non-relativistic NR. So this indicates that the method does not explicitly account for relativistic effect, which becomes important for heavier elements or systems with high electron velocities. So that's the case with the relativistic effect. But for benzene, we all know that it contains only carbon and hydrogen, or light elements. So non-relativistic treatments are often good approximation for many properties. So here in this case, we are focusing on magnetic property or magnetic field. And speaking about linear density, the LD, this implies that the response of the system to the magnetic field is treated linearly. This is generally valid for weak to moderate magnetic field strengths. This induced current and other magnetic properties are assumed to be proportional to the applied field. And then speaking about orbital dependent current density function, this is actually the most crucial part of this method. It signifies that the method considers the orbital motion of the electron to calculate the induced current density in response to the magnetic field, so that this magnetic field interacts with the orbital magnetic moments of the electrons. This is in contrast to the methods that might primarily focus on the interaction of the electron spin within the magnetic field. For example, we can say spin Zeeman effect. So, in simpler terms, how this can be used in AMS, it simulates how the electrons in the molecule like benzene move in response to an applied magnetic field, ignoring the relativistic effect. So it can assume the changes in electron distribution and the resulting magnetic properties, which are directly proportional to the strength of the applied magnetic field. So this is actually a brief description about that method, which is very important for setting up the calculations related to our magnetic field in benzene molecule. So then, after setting up all these calculations, we need to do the necessary uh, calculation running. So this is actually the input. I saved it as benzene for mf.ms is the extension of this input file. And once the job is finished, we need to view the result and how this magnetic field, how this can be visualized. So this is actually that result. And now I will show you that how we can take the result to the next level. So how we can vary this magnetic field, or how it can be helpful in giving the aromaticity. So we can observe that two parameters that to select that's magnetic as well as uh, how we can define the density. So when we open the result, this is actually the AMS view. So we have to add this vector field and streamlines. Once you add this vector field and streamlines, it will visualize at the bottom here. And if I select both, so you can see the streamline. So this red color circle is the streamline, and if you untick it, it will show you the vector field. So these two things, what are these properties? So it can observe a ring-shaped current, which is a direct consequence of the delocalized pi electrons responding to the external magnetic field, where we can visualize this as vectors or streamlines. So what is actually this streamlines and what is this meant for? So this will allow you to visualize the current density as vectors or streamlines, which will provide a compelling visual demonstration of the theoretical concept. So relating it to NMR, we need to brief that concept in the next class or next session. So speaking about the aromaticity, we can connect the observation of the ring current in the sense means this vector, and the resulting magnetic properties to the concept of aromaticity and the unique electronic structure of benzene, and how we can vary the magnetic field. So we can perform the multiple simulation with the different magnetic field strengths to observe how the induced current and NMR properties can change with the field. So this allows for a more depth in scientific investigation. So how this thing can be briefed. So this is actually the representation. Okay. So just now I'm just winding up the session. We will see with another example in the next session. Thank you.